Am I streaming? Uh, let's see. Let's see if I'm streaming. All right, I'm streaming as hell right now. Yep, I'm streaming all right. Let's see. All right. So we're gonna go over midterm study guide. I went over it with Sam, so I know a good bit. But first, we're gonna go over previously asked questions from me from my last thing, and it is so Henry's law talks about the concentration of gas in a liquid is directly proportional to its solubility and partial pressure of that gas. So it would make more sense. Um, okay, never mind. I lost my train of thought. But oxygen, if you pump more oxygen into someone's atmosphere and environment and into their alveoli, they're going to be able to dissolve more oxygen into their liquid, into their plasma in their blood. And however, we know that CO2 is 20 times more soluble in water than oxygen, even though CO2 only makes 0.2% of the atmosphere, while oxygen makes up 20%. So why is that? And I had that question. I asked him, and he said it's simply because of oxygen's chemical structure and CO2's chemical structure. So those two bits of information are not are not together. All right. Also, we had questions about ventilation and perfusion coupling. There was a couple. There was two slides about that, and they were at two different points. So it's like, oh shoot! It looks like we gotta have a pretty good understanding of this. And he basically just said that uh, it's as simple as if you don't have good perfusion, it doesn't matter how good your ventilation is. If you don't have good ventilation, doesn't matter how good your perfusion is. And basically, it's just saying the system works better as a whole if both of them are working well. All right. And next is restrictive versus obstructive uh, diseases. And it's so there was that four at the end of this stream. We'll go over those four again, just because I don't have it up right now. Uh, just because those are kind of stuff we skimmed over, but feel like it's gonna come up in a question. But anyways, restrictive makes it harder for air to come in, and so now that makes us kind of think of the processes that allow air to come in. It's when we expand the volume of our lungs. So less lung compliance would be restrictive. And obstructive is being able to get out. And that would be like airways that are airways that are blocked or whatever. And the mnemonic I'm using for those are restricted areas are hard to get in, and obstruction it's like obstructed roads, so blocked airways it's hard to get out. So that's they're kind of like the same word, but in my mind, restricted areas are so you can't get in. Uh, so that's how I make that difference in my head. Anyways, so let's just now that we got that out of the way, let's do the midterm study guide. The midterm will cover topics weeks 1 and 3. Use the study guides posted from each week. Because those have learning objectives for each week. So respiratory system, urinary system, and there's 19 multiple choice questions and two. This got updated to 3 free responses. All right. So here we got this graph. I'm gonna zoom in on this graph here. Um, so this is showing affinity. It's showing oxygen affinity. And yeah, so we see on the x-axis. So I'm just gonna try to break this down here first before we get into it, just so I'm not telling you stuff without it having any sort of context. So oxygen partial pressure is how much oxygen is floating around, and hemoglobin saturation for the y-axis is how much oxygen is being held on by the hemoglobin. So we see here at so yeah. So let's read these next. So decreased oxygen. So the decreased P50. Let me look up P50 again. P50 in the context of oxygen refers to the partial pressure of oxygen at which 50% of hemoglobin is saturated. Oh, okay. So P50 is the partial pressure needed for hemoglobin to be have to be 50% saturated. So if that were to decrease, the partial pressure needed for that were to decrease, it would increase the. It basically means that the affinity is greater, right? So just the P50 thing we haven't really been introduced to, but that's what it means. It means how much partial pressure does there have to be of oxygen in order to fulfill 50%. And if that pressure is decreased, that means that the hemoglobin has a greater affinity. If that partial pressure is increased on here on the other side by my cursor, if it's increased, if we need more partial pressure to saturate 50% of the hemoglobin, that basically means that it has a decreased affinity. That hemoglobin needs more pressure in order for it to saturate itself. So that's why. So that's what that means. Because I was having trouble understanding, so I went to Sam, but that's basically what it is. So that's how to read that. And I'll just go over it once more, just because it's an unfamiliar term that we haven't been shown yet. So P50 is the partial pressure needed to saturate 50% of a hemoglobin with oxygen. If that number were to decrease, that means the hemoglobin has a greater affinity for oxygen. If that partial pressure number increased here, that means that the hemoglobin has a decreased affinity for oxygen, right? Because you got to add more pressure, more oxygen to convince it to grab more oxygen and saturate itself. All right, so what are things that increase affinity? So lower temperatures increase affinity. And you kind of might be thinking, why would that be? Or what's a way that I can remember that? I think about how when you're breathing in air, the air you're breathing in is a lot colder than your tissues. So where would you want that rule to take place? That lower temperature increases oxygen affinity. You want it to be in your lungs so you can maximize the amount of air you're breathing. Like where would that lower temperature increasing affinity, where would that be helpful? It'd be helpful in the lungs. And obviously you want high affinity in the lungs because you're wanting to collect as much oxygen as you can. So that's how I remember that. And low carbon dioxide, you're letting go of your so the PCO2, partial pressure of CO2, If it's going down, again, you're in your lungs. Think about like your lungs, and how there's not a lot of CO2 there because you're releasing it. And so that would be a place where you would have greater affinity. And so the 2 3, so 2 3 DPG. Me and Sam went over this just trying to figure out what we need to know because he wasn't sure what the bounds were, so we had to check OpenStax for it. 2 3 DPG, as we learned in class, however, is a chemical that your red blood cells used in the first step of glycolysis to make energy. Since red blood cells don't have mitochondria, they're only just packed to the brim of hemoglobin. This is really helpful for them. It kind of takes place of a mitochondria. So that's what they use it for, because they still have their own process that they need to fulfill. And basically, he landed on the fact that you simply need to know that if there's less of 2 3 DPG, you have an increased affinity, and if there's more, you have a decreased affinity. That's he doesn't want he doesn't care whether you know why or how, or kind of explain it. It's simply that way because it is. All right, so what increases affinity is pH. So higher pH, meaning more basic, increases affinity. That also makes sense to me just because, decreased affinity, it kind of has a negative connotation in my mind. I'm like, no, because I want the most oxygen, right? But obviously we need to have decreased affinity at some points in order to let go of oxygen to fill our tissues. But I'm gonna to help solidify this in your mind, I'm gonna write on this idea that that decreased affinity is a bad thing. I also associate lower pHs, more acidic, as being a negative thing, just because you hear it all the time. How things that are acidic are damaging to you and to objects and stuff like that. So that's how I remember that. If it's really acidic, if something is more acidic, then it's gonna the hemoglobin is gonna have a decreased affinity. Why? Sam made it seem like we just got to know that. That's it. We just got to know what temperature effect does, carbon dioxide, 2 3 DPG, and pH. Just simply know if I were to affect one of those things, would it move the chart to the right or to the left? All right, so annotate the graph above with the following information. Where is the blood pH higher and lower? So the blood pH is higher on the left side and lower on the right side. Okay. Where is O2 delivery to tissues improved or inhibited? So it would be improved to O2 delivery to the tissues. We want decreased affinity so that the hemoglobin lets go of its oxygen, right? So we want increased affinity in the lungs, but we want decreased affinities in the capillaries so that we actually let go of the oxygen we've been accumulating, that we've grabbed from the atmosphere. And so where would it be inhibited? Where there's increased affinity, because now the hemoglobin affinity, it likes the oxygen, it won't want to let go. So that's why specifically the O2 delivery to the tissues would be inhibited if the hemoglobin is just holding tightly onto its oxygen. All right, so these questions I thought were different to this, because there's a line through it, but he said that these questions are relating to this photo still. So that was something that I got stumped on, so I'm just sharing that. I'm gonna drink some water really quick. All right. So give an example of a body location where you would find each curve. The way we answered this, we didn't answer doesn't make sense to what I think he misread it, and then we answered a different question because we were talking about a question, a whole different question. But let's go over it anyways. So, give an example of a body location where you would find each curve: pulmonary, capillary, systemic, and muscular arteries. What he explained to me, what we were going over, which I guess will still be helpful just so we can understand this graph better, is what type of curve would we see at the pulmonary capillaries. Here, let's pump this into ChatGPT, just because this is literally a different question that me and Sam made up a question, and then we went over it. But let's ask ChatGPT this, and then I'm gonna go over this again. So, what we went over is what pulmonary capillaries, systemic capillaries, and muscular arteries. Which one would resemble these lines? So, would pulmonary capillaries be would have an increased affinity, middle ground affinity, which isn't really you know isn't really important. Is it basically is pulmonary capillaries, are they gonna have an increased affinity or a decreased affinity? So pulmonary capillaries are gonna have a increased affinity because they want to collect as much oxygen as possible, and also we know that because in the pulmonary capillaries, the temperature is lower because it's getting exposed air. The CO2 is lower because we're letting go of it. And the 3 DPG, I don't know. We don't really need to know anything about that. And the pH, again, we don't. Uh, I don't know. But basically, yeah, that's what we came up with. Systemic capillaries, we figured would be decreased affinity because again you want to this is your systemic capillaries, it's the rest of your body, it's going to tissues, you want a decreased affinity so that you're able to let go of this oxygen. And muscular arteries, he said to just it could be both, he doesn't know, and to just write a good response about it. But anyway, so that's the question that we went over, but that's not the question that he wrote. So in this study guide, so let's see what ChatGPT got to say about it. Sure, it sounds like you're referring to and asking for examples of body locations to match the conditions of different parts of the curve. Okay, so here says moderate affinity. Muscular arteries would be like in the middle of the curve. Oh, okay. It looks like we did ask. We did answer correctly. Okay, cool. So middle of the curve would be muscular arteries. In these arteries, oxygen has already been loaded onto hemoglobin lungs and is transporting circulation and hemoglobin is still saturated but not under the stress to release oxygen yet. Okay, so that makes sense. So it's neither neither does it have a super increased affinity state, and it doesn't have a very decreased affinity state, so it's somewhere in the middle. Okay, never mind, forget it. We That is the correct answer since that's what ChatGPT said, and ChatGPT is not wrong. All right, next. So, give an example of a situation where you give an example of a situation that would cause the hemoglobin saturation curve to shift in one direction or the other, and explain why. All right. For this, he just kind of said like just think of any. This would be an example of a short answer question. So just think of any hypothetical. What would shift left or right? So I said hyperventilation. So hyperventilation would decrease what would decrease the carbon dioxide, it would increase pH, making it more basic since carbon dioxide is basic, and it would bring more air into the lungs. Um, it would make the blood more basic, and it would drop CO2, and it would also make the body colder because you're exposing more air to your body. And that's why I wrote how it would increase affinity and thus shifting it to the left. So that's just um, my example. You can think of literally any other example, something that would increase CO2, like holding your breath. Would you could write the same thing, or if you were in a super hot place, the temperature thing, or if you started consuming something that was very, very, very acidic. Any of these things could be. You could talk about any of these things, any hypothetical linking to any of these four things. That was mine. Name the gas laws at play in the graph. All right, I gotta log into the thing. Oh, never mind. Yeah. Well, I'm gonna log into my slides to see all the gas laws. I should know them all by now, but I don't. So, it's fun. It's fun. All right. Oh, cool. So we can go over the four clinical notes and classify whether they're obstructive or restrictive. Now that we have this open, because otherwise I would have been too lazy. All right. So Boyle's law. So Boyle's law is pressure of gas is inversely proportional to its volume. All right. So how does this relate to this? Uh, so I don't know, since pressure is not one of the things. Uh, uh, yeah, I'm not sure. That's something I'll have to ask him. So that's a note here. I'll take a photo. So remember. All right. So Charles' law, how is this? Oh, volume of gas is proportional to its temperature. So temperature rises. Decreased affinity because this would make sense since the everything would be more spread out, so it would have a harder time grabbing oxygens, and when it has a harder time uh, grabbing oxygens, it's not gonna have that affinity that a saturated hemoglobin has. Because remember, the more oxygens that are on a hemoglobin, the more affinity it has. So if the temperature rises and everything is pushed farther away, it's less likely to encounter oxygen, and that oxygen that would be added on wouldn't be helping to grab another one. So that one makes sense. So that's how I would write it. And so colder temperatures here in this photo would make the space smaller, and so it would be the affinity would go up since it's just so much easier to grab an oxygen. All right, next gas law. Partial pressures. Total pressures exerted by a mixture of gases equal to the sum of pressures exerted by each gas. Um, I have no idea why this would matter in this graph in specific. Because it's pretty specific to hemoglobin saturation, affinity. So I don't know. Next. I took a photo already to ask later. Henry's law. Henry's law here is important because here we can see how the higher the partial pressure, the more affinity there is here, the more saturated hemoglobin is. So we can just see that here, since it states that the concentration of gas in the liquid is directly proportional to the solubility and partial pressure of that gas. So the solubility of oxygen is higher at the oxygen partial pressure. And so we can see that that's what helps keep this hemoglobin saturation percentage high. All right, cool. Next. All right, so identify and annotate the functions of each structure in the glomerulus. So proximal convoluted tube, podocyte, afferent, efferent, distal convoluted tube, macula densa, juxtaglomerular cells, and renal nerve. All right, so we know what they do. The only things that are unfamiliar here is renal nerve and juxtaglomerular cells. So here's how it goes. This is outside of the scope of what we need to know, but it's nice to know what these extra words are. So I asked him what is the juxtaglomerular cells, and he says that that's what the macula densa are exciting. So the macula densa have chemoreceptors for salt, sodium, and once they get when they're getting activated, because there's so much sodium, the juxtaglomerular cells start creating a lot of ATP, and with that ATP, it constricts the afferent arteriole. But we don't really know that. So just what my mouse is circling here, we don't need to know. Everything else we gotta know. So what would a change in any of these structures affect the GFR or urine production? So the GFR is going to determine urine production because 1%, I think it's like 0.01% of the GFR is gonna of the GFR's filtrate is gonna become urine. So by answering the GFR, it's answering the urine production question. So all right, so let's go over that. So how would it change to these structures? So the proximal convoluted tube, if it became constricted or if it was smaller, it would create, or if it got backed up in any sorts, it would bring more water, since there's it's a bottleneck, the water's going to build up in the capsule. It would increase capsular hydrostatic pressure, which is the pressure here, my cursor, is the pressure that the liquid in the capsule is putting onto the glomerulus. 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 So that's, I say glomerulus, but whatever. Glomerulus. Glomerulus. That's how you pronounce it. Glomerulus. So that's that's the capsule hydrostatic pressure. So that's how a change in that. If it got bigger, then a lot more liquid would be able to leave the capsule, and then the capsule hydrostatic pressure would decrease, which would increase net filtration. And I guess I should mention first that there's two forces. So there's three forces at play for and net filtration. I forgot what the P is, but we know. But basically, we know. There's three forces at play. One of them is blood colloid. osmotic pressure, which is like the solutes of the blood. Since the blood has a lot of solutes, it wants to bring in blood. So that would be a force that's convincing the blood to not go into the, convincing the liquid, I should say, liquid to not go into the capsule, since it's like, okay, well, I want to hang out with the proteins and the solvents in the blood. So that's a force against diffusion into from the glomerulus into the capsule. And there's also glomerulus hydrostatic pressure, which is the pressure here on my cursor from the blood on the glomerulus. So glomerulus hydrostatic pressure is going to convince the blood to go out of the glomerulus. Since it's pushing against the glomerulus walls, it's going to push water out of it. And the third one we just covered is the capsular hydrostatic pressure. So if the capsular hydrostatic pressure were to increase and it's forcing against filtration, the NFP would drop. Since now there's a greater force against NFP. So that's how basically you're going to want to go about it for all these podocytes. If they were injured or killed or whatever, since these act as a filtrate, as a filtering piece, if they were to be gone, the NFP would go up since there's more blood colloid since there's more glomerulus hydrostatic pressure. Efferent arterial, if it were to constrict, then it would bottleneck that too, basically at the very end, and it would just kind of push back water into the area. And so yeah, these are all kind of logical. And if you like, there's no like, if the afferent gets tighter, then NFP is going to drop because there's now less fluid. Oh wait, no. NFP would. Never mind. I'm getting confused here. Ignore me. Basically, just sound it out. Ask ChatGPT because these are pretty intuitive on what changes to them would do to NFP. So NFP constricts, bottlenecks, increases NFP since there's more blood hydrostatic pressure. Dilate. So yeah, take a photo of that just because I have another question about it. Oncotic pressure. So we know what hydrostatic pressure is. It's the pressure of the water pushing on its cell walls. It's like the pressure of water against the tube it's running. Oncotic pressure is like it's basically blood colloid osmotic pressure. But oncotic is specifically about proteins. So basically, oncotic pressure is that pressure of blood of liquid wanting to hang out with albumin, the proteins in blood. That's it. So if you're familiar with blood colloid osmotic pressure, oncotic pressure is the same thing, but oncotic just is very specific about proteins. But the solutes in blood are proteins, so that's why they're kind of the same thing. At least most of the solutes in blood are proteins. So describe how NFP is determined. Yeah. Let me look at the GFR. So yeah, that's just for that last question. It's equal equation. Why is this the word here? This is the net filtration pressure. So just basically understand this. That's it. So here's net filtration pressure is equal to glomerular blood hydrostatic pressure minus capsular hydrostatic pressure plus colloid osmotic pressure. That is it. But now I'm confused about the GFR urine production. Okay, so they're basically the same thing. So essentially, NFP determines how much fluid moves across the glomerular membrane into the Bowman's capsule because it is NFP represents the driving forces behind filtration, and GFR is the result of the filtration process, as in measures the rate of which blood is filtered. So one of them is the rate of volume, and the other one is driving forces. So NFP is forces, and GFR is just volume rates, which makes sense because GFR is glomerular filtration rate, while NFP is P standing for pressure, net filtration pressure. So that makes a lot more sense. Okay, so yeah. So now that is it, guys. We did it. We made it. It's never over. Okay, so next I'm gonna ask ChatGPT, are these obstructive or restrictive tuberculosis, emphysema, asthma, and cystic fibrosis? No, I don't want to download that. Okay. So tuberculosis, it says, is the only restrictive one. However, cystic fibrosis is obstructive and can be mixed. So that's the one that was a little weird. So let's go over these. So emphysema, airway sacs are damaged, making it hard to inhale. So that's obstructed. Emphysema, obstructive. To exhale fully, because obstructive again is hard to get out. Asthma is also obstructive. So airways narrow due to inflammation. So again, air obstruction to the airways was like obstruction to road, like an obstruction to a road. Obstructive is hard to get out. So that makes sense. Cystic fibrosis is a thick, sticky mucus clogs airways. So since again we're blocking the airways, it's hard to get out, it is obstructive. Though over time, scarring from the cystic fibrosis would affect the lungs' compliance and make it restrictive, since it's also hard to get air in if your lungs can't fully expand. Makes sense. And tuberculosis causes scarring in lung tissue and reduces lung compliance and limits lung expansion, making it hard to breathe in. Okay. That is all I needed to know. Now it's in there. Anyways, guys, I think that's it. We went through this whole thing and we answered some questions that I had about the slides. And if you guys have any questions, you guys can text me on our GroupMe group chat, and I will respond and I will cover it in a live stream. So yeah, let's see. Okay, guys.